So here we are in the last part of the lecture. We are going to see half-range expansions, and mainly the idea is we have a function f defining on the interval 0p, and we can think about this interval 0p as half of the interval minus p, and we can choose how to work with this function in the sense that, okay, I have a function f in this interval 0p and I want to get an even function. Okay, the only thing I have to do is extending this f to the interval minus pp in an even way, and then we will see how we can do that. And if I want to get an odd function, the only thing I have to do is, okay, I have this function in the defined in 0p. I will extend this function in an odd way in the interval minus p. So the idea is that given this function in this, let's say, half interval, we can choose how to extend it in interval minus p in such a way that we have an even function or an odd function. And in those cases, we just saw in the previous part of the lecture that it's easier to compute the Fourier series representation in these cases. Okay, so what I was saying, we can choose how to extend f on the interval minus pp. For instance, such that f is even. So if we start with this function f here, if I want an even extension, I just have to copy the graph of f in such a way that is symmetric to the y-axis. If I want an odd extension, I have to take the graph of f and copy it in such a way that in the interval minus p0 we have a symmetry but with respect to the x-axis. Okay, so this is in the graph setting, but how about the definition of the function? So how to extend the function f defined in 0p, in the interval 0p. So the even extension is, okay, I have f given in this interval, and then I want this new function g to be even, so I just put the right thing here to verify the definition of being even, which is exactly f minus x, f of minus x, where x now belongs to the interval minus p0. And then we need a periodic function to have a Fourier representation, so we have only to repeat this function itself in the outside the interval minus pp, which length is the length of the interval minus pp is 2p. So for the even extension, given the f in the interval 0p, we just put in the, we reflect this function in the interval minus p0 with this value here, f of minus x, and this is exactly what makes the function even. And this guy makes the function 2p periodic, the function g. Okay, the odd extension, we have the f given in the interval 0p, and we put here exactly what we need to verify the definition of being an odd function, which is minus f at minus x, where now the x belongs to minus p0. So these guys make this function g an odd function, and this line makes the function g a 2p periodic function. And 2p is exactly the length of the interval minus pp. Okay, so given a function f in the interval, defined in the interval 0p, f has a cosine series expansion given by this expression, where we know, since we saw in the second part of the lecture, how to compute these coefficients when we are working with an even function. And this is called the cosine series expansion of f. And the function f has a sine series expansion in this way, where we know how to compute these coefficients because that's what we saw in the previous part of the lecture. And these are also called the half-range expansions. Okay, so when we are talking about the half-range expansion of f, we are talking about these two guys, the cosine series expansion and the sine series expansion. Okay, so for x in the interval 0p, the cosine or sine series expansion coincides with f of x when f is continuous at x, and this average that we can also think about like the jump in the graph when f is discontinuous at f. Remember the notation, that was the average of the right and left limit, and the limits are when we approach x from below and when we approach x from above. Okay, so example. Find the half-range expansions of f exactly x, for x between 0 and 1. So, half-range expansions, we mean, when we are saying half-range expansions, we mean that we have to find the cosine series expansion and the sine series expansion of this f. So, again, given an f in this, let's say, half interval 0, 1, we can extend this f in -1, 0 in this, at least in these two ways, in an even way and in an odd way. So let's start with the even. This is the graph of f, just the identity here. And okay, for the even extension, we have, this is the definition of the even extension that we just gave a couple of minutes ago, where this part makes the function even and this part makes the function two periodic, because we start with this interval of length 1 and we want, and if this is the half of the interval of a new interval, then we have to extend this with another interval of length 1, and that's why we will get the -1, 1 as the main interval. So we have x and minus x, just following this definition, where now the value, so here p is exactly 1, okay? And if we want to think about the graph of the even extension, as we were saying maybe many times, we take the graph of f and we copy it in such a way that it's symmetric to with respect to the y-axis. Okay, and then since the function is periodic, we just repeat this graph all over the line. Oops. Okay. And as we said, this is the length of the total new interval is 2, and the interval is -1, 1. Okay. Now we know that the corresponding half-range expansion for the even extension of x is given by this expression, where we only have a0 and an involved and the cosine functions. Here p is equal to 1, and we know how to compute these coefficients because we saw that before. So the first one, a0, is just the integral of f between 0 and 1, and f is simply x. So this is an antiderivative of this function, and we evaluate this between 0 and 1, and we get this 1/2. So we already know the value of a0. For an, we know from the formulas that we saw before that this is 2 times the integral from 0 to 1 of x and cosine of n pi x. Again, we use integration by parts. We can call this u and this b prime. And then here we have an antiderivative of b prime. So b can be this guy. And here we have u, and then u prime, which is 1. That's why there is nothing there. And this is b. And integrating, computing here, you get 0. And integrating here, you get this guy. And we have this constant in the front. And we can put together this minus and this minus to get a plus here. And that's why there is no minus here. And cosine of n pi x in 1 is exactly this guy. And cosine of 0 is 1. Oops. Okay. And we saw also before that for even values of n, this is exactly 1. And for odd values of n, this is exactly -1. So we can rewrite this cosine of n pi as -1n to the power n. And now if we look at this expression, which is this guy here, we can compute that for when n is 2, 4, 6, and so on, so even, this is exactly 0 because we get a 1 here and a 1 here, -1, so we get a 0. But with when n is equal to 1, 3, 5, 7, so it's odd, we get a -1 here and a -1 here, so we get a -2. So putting this information, going back to the computation of the coefficient an, what we get is 0 when n is even, and -4 over n squared pi squared if n is odd, because we get a -2 from this part, and we already had this 2 over n squared pi squared there. Okay, so summarizing, this representation, which is the half-range expansion of f, the cosine series expansion of f, we can write this properly because we already found the coefficients a0 and an. So a0 was 1/2, and here we have an. And okay, we knew that for n even, we have 0. So we can write this series in this way. We change the parameter here. The indexes now are called k. And we only take the odd values, and we can write this in this way. We consider 2k plus 1 from k from 0 to infinity, and these guys are only taking the values 1, 3, 5, 7, and so on and so on. When k is 0, this guy is equal to 1. When k is 1, this guy is equal to 3, and so on and so on. This is a nice way to write that we know that this coefficient is 0 for even values of n, and well, this number for odd values of n. So take into account this way of rewriting these figures. Okay, and this is the n in this case, which is odd. And if you want this value, which doesn't depend on k, we can put it in the front, but it's not mandatory, it's just a comment. Okay, that was the half-range expansion of f with cosine. So the cosine series expansion of f. we started with an f, only defining in the interval 0, 1, and we extended it to the interval -1, 0 in an even way. And obviously periodic to have the Fourier series expression, representation. Okay, so last part, the odd extension of f. Here we only put the definition that we gave before. Again, this part is only to verify that we are working now with an odd function, an odd extension of f called h, and this guy gives us the periodicity of the function. This is what we have to put here to verify the definition of being an odd function. And in this particular example, we have f equal to x. So this guy is minus minus x, which is exactly x. So what we get is that this odd extension is the function x if we are in the interval -1, 1, and then we just repeat this graph, this definition of the function itself outside the interval to have a periodic function of period 2. So how is the graph of this extension? So this was the graph of f, and now we are extending this in a symmetric way, but with respect to this guy, the x-axis, because we want the odd extension. And since we have this periodicity, we just repeat this graph all over the line. Okay, now the corresponding half-range expansion for the odd extension of f is given by this guy, where we only have the coefficients bn and the sine functions. And we know how to compute this bn is 2 times the integral from 0 to 1 of f and this sine function. X is just x, and we have this sine function here, again by integration by parts. So we are not going to see all the details here because maybe the computations are quite similar, because the functions that are involved are this sine and cosine that at some point you will get used to integrate and differentiate these functions. And then using integration by parts, we get this expression. Here we can compute this guy, which gives us 0. And here we find again this expression, cosine of n pi, that we already know that we can rewrite this as -1 to the power n, because for n, when n is odd, this is -1, and when n is even, this is 1. That's why we have this expression here. And with this minus here, we can put the plus here, and finally get this expression for the coefficient bn. Okay, so therefore we have this the half-range expansion of f, the odd half-range expansion of f, also called the sine expansion of f, is 2 pi, because we can also put this number outside the series, because it doesn't depend on n. That's an option, it's not mandatory. And this guy here, -1 to the power n plus 1 over n, and the functions sine and pi of x. Okay, so this half-range expansion of f, and in general all the Fourier series properties that we saw in this lecture and the previous lecture, will be super useful when we need to solve partial differential equations. So it's always useful to check also if we are working with even and odd functions. So we have this simplification of how to compute the Fourier coefficients. Okay, I think that's it for today, and you can some of the topics that we were talking about this lecture and part of the sections 2.3 and 2.4, and those are the exercises, but again, this information will be also on Blackboard, so it doesn't matter now. That's it for today.